Motors are a key component of the power system. The switched reluctance motor provides an alternative to the traditional induction machine. Ideal applications for switched reluctance motors include looms, oil pumps, presses, particularly brick presses, mining machinery, and conveyor systems. Switched reluctance motors have many advantages, which allows them to overcome some of the problems which are associated with induction machines, particularly those with variable speed drives. But how are switched reluctance machines different? The product is a combination of the switched reluctance motor and its drive. Neither will work without the other. The switched reluctance motor has a simple, rugged structure. The rotor is simply made of laminated metal. There are no permanent magnets or windings, making it very reliable and relatively low cost. The design also features a solidly built stator with very simple windings, which allow for the high-speed operation of the motor. The switched reluctance motor has the ability to change rotational direction frequently. If it has suitable braking power, it can start and stop up to 2,000 times in an hour. The motors can quickly adapt to changes in the load by adjustments to the sampling rate, thus giving them excellent dynamic response. Now let's take a look at how the system works by considering a cross-section of the motor and a simplified version of the control unit. The diagram shows a motor with a 12-8 configuration. This means that the stator has 12 salient poles and the rotor has 8. The direction of rotation of the motor is dependent upon the order in which the poles are energized. It is completely independent of the current direction. The poles on the stator of the motor are divided into 3 groups. The windings on the poles within each group are connected together, so all of the poles in that group will be energized simultaneously. Initially, the poles of the rotor are aligned with the stator poles within the A group. The supply is then switched from the A to the B windings. The rotor then rotates until it aligns with the B windings. Supply then switches from the B to the C windings. Then the cycle repeats and the motor continues to rotate. The energization of the windings is controlled by the controller unit, which can also change the speed and direction of rotation of the motor. This diagram shows a switched reluctance motor employed as a pump. A pressure transducer feeds back to the controller. If the pressure changes, the controller can automatically adjust the speed of the motor to compensate. But why use switched reluctance motors when induction motors are so widely applied? Control of induction machines is usually achieved with a variable frequency drive. To see why switched reluctance drives may be preferred, it's necessary to see why in some cases the application of the induction motor is not ideal. The induction machine is perfect for applications where it can start with a relatively low torque and where its speed and load are constant. However, for high torque starts, slow speed operation and variable torque, the performance is not so good, leading to overheating and reduced efficiency. This is illustrated by a comparison of the relative efficiency of an induction motor controlled by a variable frequency drive and a switched reluctance motor. We can see that at low speeds the switched reluctance motor is more efficient, but the difference between them narrows as we approach rated speed. Now let's take a look at the variable speed drive. In this example, the supply to the motor is a 3-phase AC voltage. The first stage of the control mechanism is to rectify the voltage. The rectified voltage is then smoothed. An inverter then chops this smooth signal to recreate an AC waveform. By varying the frequency of the inverter, the value of the voltage to the motor can be changed. Of course, the supply to the motor is not a true sinusoid, but is an approximation created by power electronic switching. This results in a slightly distorted waveform which is further affected by harmonics, resulting from the rectification in the switching frequency. This leads to a reduction in efficiency of the motor and increases in its temperature, noise and vibration. In addition, the drive appears to the network as a nonlinear load. This produces harmonics on the supply. The unwelcome effect on the power quality of the system may have to be dealt with by installing complex and costly equipment to remove the harmonics. In some cases, power company rules might make this compulsory. The absence of high frequencies on switch reluctance machines makes such equipment unnecessary. Another problem which may be encountered is that capacitance within the motor may provide a path for the high frequency signals. As a result, current may flow through the bearings to the earth. This phenomenon, which is known as bearing current, can result in pitting in the ball race, which in turn affects the efficiency of the machine. A further drawback of induction machines is the very high starting current which they may draw. This will introduce difficulties in making the settings on the protection. It could result in voltage dips on the system and is likely to require an increased rating on the supply, which may not be possible if the machine is driven from a renewable source. None of these issues affects the switch reluctance motor, which can be used for many applications where the induction machine is not suitable. Kahui Power Automation is a major manufacturer of switch reluctance motors and drives, producing several thousand sets each year. For more information, contact us through our website www.kahui.com.